In 1948, a 30-year-old physicist sat down at a chalkboard at Cornell University and wrote a formula so strange, so impossibly powerful, that mathematicians today still argue about whether it's even legal to use. His name was Richard Feynman. The formula was the path integral. And here's what almost no one tells you about it. Feynman didn't set out to prove the multiverse exists. He wasn't trying to validate science fiction. He was just trying to fix a problem in quantum mechanics. But the equation he wrote down has a side effect, a quiet, terrifying implication buried in its math, that the universe you're sitting in right now is only one of an infinite number of universes that all happen simultaneously to bring this exact moment into existence. By the end of this video, you're going to understand exactly why some of the most respected physicists alive believe Feynman's path integral is the closest thing we have to a mathematical proof of the multiverse. And you'll also hear the strongest argument that they're completely wrong. Let's go deep. To understand the path integral, you have to understand the problem Feynman was trying to solve. In the early 20th century, quantum mechanics had a working equation, Schrödinger's wave equation. It worked. It predicted the behavior of electrons. It got the atom right, but it had a philosophical hole in it the size of a galaxy. The wave equation described particles as waves of probability. It told you where a particle might end up, but it could not tell you in any clean way how the particle got there. In classical physics, this question is easy. You throw a ball, it follows a curve through the air. You can trace its path. In quantum mechanics, that whole idea breaks. Ask where an electron was a microsecond ago, and the answer is essentially, it was nowhere in particular. It was a smear of possibility. Feynman hated that answer. He wanted a version of quantum mechanics where you could talk about paths again, real physical trajectories. He picked up a forgotten 1933 paper by Paul Dirac that hinted at a deeper idea, that the laws of quantum mechanics might secretly emerge from something called the action, a quantity from classical mechanics that measures how a particle moves through space and time. Feynman took that hint and ran with it. Here's what he came up with. Imagine an electron has to travel from point A to point B. Classical physics says it takes one path, the shortest one, the lazy one, the path of least action. Schrödinger's equation says don't even ask, just calculate the wave. Feynman said something completely different. Feynman said the electron takes every possible path at the same time, not just the straight line, not just the curve, every path. The path where the electron flies straight there, the path where it loops around the moon first, the path where it shoots out past Andromeda and comes back, the path where it goes backwards in time, sideways through space, and then forward again. Every conceivable trajectory, no matter how absurd, contributes to the final answer. You sum them all up, every single one. Infinite paths. And what comes out the other side of that sum is a probability, the probability of the electron arriving at point B. This is called the sum over histories, and it is the most powerful equation in modern physics. Now I know what you're thinking. This sounds insane. It sounds like a math trick, but here's the part that breaks people's brains. It works. It doesn't just work, it gives the exact same answers as Schrödinger's wave equation, down to the decimal. Every prediction Schrödinger's equation can make, Feynman's path integral can make. They are mathematically equivalent. They are the same physics. But they tell two completely different stories about what reality is. And this is where the multiverse enters. Here's the question that haunted physicists from the moment Feynman published this in 1948. If the math works because we sum over every possible path, if you have to include the paths where the electron goes to the moon and back to get the right answer, then in what sense are those other paths not real? Think about it. The interference pattern in the famous double-slit experiment, Feynman's path integral explains it perfectly. The electron goes through both slits, because in the sum over histories, it goes through every slit, takes every path, lands at every point. The pattern you see on the detector is the leftover signature of all those paths interfering with each other. That interference pattern is real. We measure it in labs every day, which means the paths that produced it had to be real enough to interfere. If they were real enough to leave a measurable mark on this universe, are they not in some sense universes themselves? This is exactly the question that a graduate student named Hugh Everett asked at Princeton in 1957. And here's the part of the story almost no one tells you. Hugh Everett and Richard Feynman shared the same thesis advisor, a man named John Archibald Wheeler. The same Wheeler who coined the term black hole. The same Wheeler who advised both of them, separately, in the same building. Feynman built the path integral, sum over every possible history. Everett, sitting one floor away, took it one step further. He said, "What if those histories don't just contribute to the math? What if they all actually happen? Every possible history of the universe, every coin flip, every electron jump, every choice. All of them. Real simultaneously in branching parallel realities. This is the many worlds interpretation." And by Everett's own hand, it was a direct descendant of Feynman's idea. Here's the kicker. Feynman himself, late in his life, is reported to have privately accepted some version of many worlds. The man who built the formula apparently looked at what it implied and thought, yeah, maybe that's just true. And modern physics has only made the case stronger. When we use the path integral in quantum cosmology, the physics of the universe as a whole, something incredible happens. The same mathematical machinery that sums over every possible path of a single electron starts summing over every possible history of the entire universe. Different big bangs, different physical constants, different versions of space-time itself. The path integral, applied to cosmology, gives you a multiverse for free. It's not bolted on. It falls out of the math. This is why physicists like Sean Carroll, David Deutsch, and Max Tegmark argue that the multiverse isn't really a separate hypothesis you have to add to physics. It's what physics has been telling us all along, if we have the courage to take our own equations literally. But, and this is important, this is where I have to be honest with you, not every physicist agrees. Not even close. Sabine Hossenfelder, one of the sharpest critics in modern theoretical physics, has pointed out repeatedly that the path integral being mathematically equivalent to Schrödinger's equation is exactly the reason we cannot conclude the multiverse from it. If two completely different stories, one with parallel universes, one without, produce the exact same predictions, then physics has no way to choose between them. Choosing many worlds becomes a philosophical preference, not a scientific result. There's also the testability problem. A multiverse, by definition, contains universes we cannot reach, cannot signal to, cannot measure. If a theory predicts the existence of things that can never affect any experiment we run, is that theory really doing science? Or is it doing metaphysics with equations on top? Feynman himself, despite his alleged sympathy for many worlds, was famously hostile to philosophical speculation. He once said that the philosophy of science is about as useful to scientists as ornithology is to birds. He didn't want his path integral interpreted as a multiverse machine. He wanted it interpreted as a recipe, a set of rules that gives the right numbers when you plug in the experiment. So which is it? Did Feynman accidentally write down the proof of the multiverse, or did he write down the world's most successful accounting trick? Here's what I think. The path integral does something no other formulation of quantum mechanics does. It treats every possibility as ontologically real for the purposes of the calculation. You can call that a mathematical convenience. You can call it a deep truth about reality. But you cannot make the math work without summing over those alternative histories. They are doing real work in the equation. They are leaving real fingerprints on real experiments. And once you accept that, you're left with a choice that physics cannot make for you. Either reality is a single thread, and the alternative paths are some kind of mathematical ghost story we tell ourselves to get the right answer. Or reality is the sum of all those threads, and what you call your life is one branch of an infinitely branching tree, where every possibility plays out somewhere. Feynman's path integral doesn't force you to choose the multiverse, but it removes every reason to deny it, and that by itself may be the most important thing a physics formula has ever done. The next time someone tells you the multiverse is just a Marvel movie, remember this. The single most predictive equation in all of science was built by summing over every possible reality. It works because we include them all, and nobody, not Feynman, not Schrödinger, not anyone alive today, has ever found a way to do the math without them. Maybe that's a coincidence. Maybe it's the universe trying to tell us something. If this video opened up a door in your mind, do me one favor. Hit subscribe. We go deep on physics every week. The equations, the history, the implications nobody talks about on cable TV. Tell me in the comments, do you think Feynman accidentally proved the multiverse, or is it just elegant math? I read every comment. This has been Physics Deep. I'll see you in the next universe.